This is going to be really, really cool. So this week I want to talk about something that I've been working on for a few months now, and it's a few years from completion, but this is going to be a really fun project, and I'm really looking forward to this. As many of you know, I am a college student currently studying aerospace engineering, and trust me, this project is right up my alley. I am now part of a team here at my school competing in the Base 11 Space Challenge. This challenge is a challenge to colleges and universities to develop a single-stage, liquid-fueled rocket that can fly past the Kármán line, which is the official definition of space. You heard that right. I am on a team developing a rocket that will go to space. This is no joke. We're actually doing this. An important clarification is the difference between space and orbit. Orbit is where the International Space Station is. That is up at about 400 kilometers, whereas the Kármán line, what we are trying to reach, is about 100 kilometers. But there's a much larger difference. Reaching the Kármán line just requires going straight up to about 100 kilometers, and then coming back, most likely under parachute. Orbit requires going up to about 200 kilometers, because the atmosphere is still fairly thick, relatively, at 100 kilometers. 200 kilometers, it's thin enough that you can achieve a stable orbit. But at 200 kilometers, you have to then accelerate sideways to a speed of about 9.8 kilometers per second, which is really fast. For those of you who think in miles instead of kilometers, that's an altitude of about 124 miles, traveling at a speed of about 4.8 miles per second. By comparison, space straight up is at about 62 miles. So there's a big difference between orbit and space. We are not going to orbit. That requires not only a larger rocket, but also a lot more advanced guidance. And technically, once you get into the guidance of orbit and actual trajectories, more than just going straight up, you get to a point where it's classified as a missile, and the government doesn't like that. So why is sending a rocket to space a big deal, other than the fact that it's a rocket to space? The thing is, yes, it's been done before, but not in this context. Professional organizations like NASA or SpaceX or other government agencies in other countries or major aerospace corporations, they've all done things like this. NASA sends rockets up to the Kármán line all the time, in the form of sounding rockets. Professional aerospace organizations like SpaceX and Blue Origin and United Launch Alliance have all placed things in orbit fairly routinely. But a civilian or amateur organization hasn't. Quickly, I want to clarify that my use of the terms amateur rocketry and civilian organization are very loose terms. Companies like SpaceX or United Launch Alliance are run by civilians by the legal definition. They're not military, but they are they're multi-million-dollar professional companies who hire the best of the best engineers to do things like this. So they are civilian organizations. I mean, people who aren't employed by SpaceX or things like this. They're more everyday people like you and me. That's what I mean by a civilian organization. And in terms of amateur rocketry or amateur rockets, I mean the same thing. Everyday people like you and me. They are, in contexts like this, they are by no means amateurs. People who have done things like this have actual degrees in aerospace engineering. The first civilian organization to launch something into space was the Civilian Space Exploration Team, with the launch of their rocket Go Fast in 2004. They are the only, as far as, I should clarify, everything I'm saying here is as far as I am aware. Things may have happened that I'm not aware of, but as far as I am aware, CSXT is the only civilian amateur rocketry association that has placed anything in space by passing 100 kilometers, the Kármán line. They did that in 2004 and did it again in 2014. And they did that with a solid rocket motor, which is a lot simpler than a liquid motor, what this challenge requires. An important clarification is the difference between a solid and liquid motor. A solid motor has absolutely no moving parts. It's just a fuel and oxidizer mixed together into kind of a graphite-like substance. It's solid, or in some cases like a rubber-like consistency. And you just light that and it burns until it's all gone. You can't turn it off, but once you light it, it's going, and it's very, very difficult for that to go wrong. They're very simple. By comparison, liquid rocket motors have a lot of moving parts. They use liquid fuels, usually a bipropellant of a fuel and an oxidizer. They are very complex. They require very careful design. They can be turned off and back on again if designed properly. And because they deal with liquids instead of a solid casing, they do have to find a way of getting the liquid fuels from storage to the engine, which requires moving parts or really ridiculously high-pressure tanks. So like I said, the only organizations that have done this have done it with a solid motor, and by organizations I mean a singular organization, the Go Fast rocket, or CSXT, the CSXT organization. Now I should clarify, other organizations have claimed to have passed the Kármán line, but CSXT is the only one I'm aware of that was ever officially verified to have passed the Kármán line. So that's part one of what makes this challenge really difficult. There are really three main parts of this challenge that make it really, really challenging. Part one is the fact that you have to reach space, and only one civilian organization in history has ever done it. That's part one. Part two is the fact that it has to be a liquid motor. CSXT did it with a solid. Liquid motors, like I said, are really complex and really hard to engineer. Part three is that this challenge is specifically to student organizations. Again, CSXT was a group of engineers. They were not students. This was not a university. These were quote-unquote professional engineers in a non-professional organization, I guess you could say. So, this challenge, in this context, a university using a liquid motor going to space, has never been done. In terms of accomplishments that universities have done, the University of Southern California launched a rocket named Fathom 2 that reached an altitude of about 44 kilometers, if my math is right. About 44 kilometers. That's not even halfway to space, but that is the record for highest altitude of a student-designed and built rocket. So, to ask a university to put something in space when no university has done it, and only one university or one organization has done it at all, is quite a tall task. And then you throw on top of it the fact that they want us to do it with liquid motors. Just brings that challenge to a point that, how the heck are we going to do this? Now, an important point I want to make is that there are organizations trying to do this with a liquid motor. Specifically, Copenhagen Suborbital. They are trying to launch a person into space. Again, space being 100 kilometers, not orbit. They are developing liquid motors for their vehicles, and they have actually operated quite well. They're functional engines. But the highest any of their rockets has flown, as far as I have seen in my research, the highest any of Copenhagen's orbital's rockets have flown is only a few kilometers. The highest I found so far was about 13 kilometers. So recap, what have people done? Have a civilian organization put an object in space that they launch themselves. One group has done it, CSXT, with GoFast. Have a university do it. Record is 44 kilometers. Both of these were done with a solid rocket motor. Has not reached space for a university. University record is 44 kilometers. Part 3, the liquid engine. Nobody has done this. No university has, or actually a few universities are developing liquid motor rockets, but none have come anywhere close to space. So that's where we're at in terms of what has been done. How about why? Why has nobody done this? Why is this so hard? For one, it's literally rocket science. I should point out, this is the rules say it has to be a single stage vehicle. That means a single engine, a single fuel tank, a single vehicle that doesn't separate, into multiple parts and light another engine. It has to go straight up to 100 kilometers. By comparison, the altitude that most commercial aircraft fly at, about 30,000 feet, is about 11 to 12 kilometers. We're aiming for almost an order of magnitude of 10 times higher, so almost 300,000 feet. Okay, quick math. 100 kilometers, the Kármán line, is 328,000 feet. So that is 10 times higher than most commercial aircraft fly at. We're going really, really high on a liquid motor developed by a university team. What? So what exactly are the challenges of putting an object in space with a single stage liquid fuel? How many times am I going to say that sentence? So the big problem is weight. If you're doing a single stage vehicle, what you leave the ground with has to go all the way. So you're carrying every single kilogram of empty tank that was originally full at liftoff. With multi-stage rockets, you drop those empty fuel tanks as you go, thus having to accelerate less mass and getting more and more efficient. That's not a luxury we get. We have to take everything with us, as the rules say. Single stage rocket. The other part of this is guidance. You might think it's simple of, just point straight up and just go. Yeah, it's not that easy. How do you tell a rocket which way is up? The easy solution is, gravity is down, so the opposite direction is up. Yeah, well, when you have a rocket engine running and you're accelerating, that kind of messes with which way a sensor would think is down. If you're accelerating left at 1 Earth gravity, then the resultant, as physics would call it, would be at a 45-degree angle. So acceleration means you can't base down or up based off of, sensing gravity. What it comes down to is you just have to get what's essentially a gyroscope and just orient relative to space itself, to essentially orient to reality what is up at that particular instant. It gets very, very complicated to define what up is. Why do we have to go straight up? Well, when you're going 100 kilometers, if you're ever so slightly tilted in one direction, you're going a lot further. And when rockets like this, every little bit counts. So we need to point as close to straight up as possible. Also, the rules state it has to be aerodynamically stable to a caliber of 2, which means if there's any gust of wind, the rocket is going to want to point into the wind, which means we have to somehow fight against the wind if there is any, and manage to point straight up. So guidance is going to get really, really difficult. On top of that, we have the fuel tanks. We have to carry a lot of fuel for a mission to space, and we have to find a way of storing that. The best fuels that you can use for a mission like this are cryogenic, which means they have to be stored at really, really cold temperatures. So you have to build tanks that can hold a lot of fuel at really, really cold temperatures, and depending on how you design your rocket, you might even have to store that at really, really high temperatures, such as 50 times atmospheric pressure or higher, which is just, that's a lot of energy in one space, and that scares me a lot. So now on to my favorite part of this whole project. I am the head of propulsion on the team, which means the rocket engine is my problem, and it is easily the most complicated thing on the entire rocket. It's the only thing that really has any moving parts. It has to deal with the highest temperatures on the rocket. It will have to deal with the highest pressures on the rocket. It's easily the most complex system on the entire rocket. To give an idea what we're working with, we have to take very, very cold fuel and oxidizer on the order of, a few hundred degrees below zero. Take that, dump it into a fuel chamber, burn it at a temperature a few thousand degrees above zero, hotter than the melting temperature of most, if not all, metals, and then exhaust that now burnt fuel that is now gas, exhaust that gas through a nozzle in such a way that it exits the rocket at multiple times the speed of sound. And it has to do that in a way that it doesn't blow itself up. Oh, and did I mention that the combustion chamber, where that flame is, or where those fuels are being burned, has to operate at multiple times higher than atmospheric pressure. A reasonably low efficient engine would run at least 5 atmospheres of chamber pressure. A decent efficiency engine would operate closer to 80 atmospheres. One of the rocket engines SpaceX is currently developing, which would set the record for chamber pressure, is going to operate at about 300 atmospheres. The orders of magnitude of pressure and temperature we're dealing with here are just crazy. Another fun part is figuring out exactly what temperature you're using, because few degree changes change what size certain components of the rocket have to be. So it's like, okay, simple math, if we burn the fuel at this temperature, the nozzle has to be this diameter or whatever. Okay, what temperature is your flame temperature? Well, that depends on your fuel injector temperature. Okay, what temperature is that? Well, it depends on how you're cooling the engine. Because, like I said, we're burning the fuel higher than the melting point of most materials, so we definitely need to cool it in some way or it will blow up. We don't want that. So, cooling. There's a lot of ways to cool an engine. Most of them get really, really messy in ways that the engine will either never be reused or it really hurts the performance of the engine. The best way to do it is regenerative cooling. That runs the fuel through the engine to heat up the fuel and cool down the engine at the same time. What that means is when you raise the temperature of the fuel before injection, you raise your combustion temperature, which increases your efficiency. So regenerative cooling gets you 2 for 1. You cool your engine below melting point, and you get a boost in efficiency. But the fun part is your combustion chamber influences your injector pressure, which thus influences your combustion temperature. It's a loop. And that also influences the surface area of your engine, which also affects your injector temperature. Everything depends on itself, which is essentially how the equations work out, which means it works out to be a really big headache. Now, I want to point out that this is all entirely doable. but amateur rocketry associations really haven't done this. It took NASA years to figure out how to put things in space. It took people years to figure out how to develop liquid engines. Keep in mind, these are all people that had actual degrees. These were, the top of their field. We are college students. Oh, and did I mention the timeline? We have to launch by December of 2021. That means we have less than 3 years to do this. We are not professional engineers. We are not people who do this every day. We are college students. We have less than 3 years until the window closes. I should have mentioned this earlier, but there are 4 launch windows in which we can launch in. May 2020, December 2020, May 2021, and December 2021. So the time scale we have working towards is very, very tight. It's a very aggressive schedule. To have college students, not professional engineers, college students, working to develop some of the most complex technologies developed, which, might I add, are government-restricted technologies, because while rockets may not count as a weapon, they count as a weapon delivery system, so they're classified under ITAR restrictions, which means there are a lot of restrictions on the technology we're using, which adds another headache. So yeah, we have technology that took professional engineers years to develop, and you're asking college students to do it in 1 to 2 years? Okay then. This is gonna be a wild ride. So yeah, you can tell this is going to be really, really difficult. A lot of the information that we need is kinda out there. I mean, this has all been done before, but it's not algebra. It's differential equations. It's not easy by any stretch of the imagination. It is, what we're trying to do has never been done before. No college university has ever launched a rocket to space using a liquid motor. It's never been done, and we're trying to do it in less than 3 years. It's crazy, but we're doing it because this is really, really exciting. I mean, if we can do this, we'll have done something nobody has done. We'll have developed an incredibly complex system as college students. Now that's something you can put on your resume and practically get any job you want. So I'm incredibly excited about this. I have absolute faith that we will do this. The only question is, will we do it first? Will we win the competition by launching a rocket to the Kármán line before anyone else? Or will we be the 5th or 10th team to do it? Honestly, from my perspective, I don't really care that much about doing it first. I mean, yes, it would be nice to win the competition. It would be nice to say we were the first college university to launch a rocket to space. That would be an awesome title to have. But from my perspective, I'm not doing this to win the competition. I'm doing this for the experience. I'm doing this to do it. The way I see it, if I'm applying to a job and I write on my resume that I was part of this project and that it succeeded, they're not going to care if we were the 1st or the 10th team to do it. They're going to care that we did it, that we built this rocket, that we gained this really valuable experience. That's the important part, is learning from this project. So, yeah, this is going to be a really, really fun project. I am really excited about this. I know this video was a bit longer than most of my other videos, but this is a really, really complicated thing that we're trying to do, and as you may have noticed, I'm really, really excited about this. This is going to be probably the thing that defines my career, and it's awesome. So with that, I want to thank you guys for sticking with me through this video. I want to thank you for watching. If you guys have any questions about this project, feel free to drop them in the comments below. I will try to answer them. If you want to keep up with what my team is doing, we are Florida Tech Rocketry. We hope to have a website up in the near future. Not really sure when, but when we do, I will definitely mention it here on this channel. So again, I want to thank you guys for watching. If you enjoyed this video, hit that like button. If you have not subscribed to this channel yet, go do that. I'm sure you will like the other things you find on this channel. And I want to remind you guys, my videos come out every Thursday at 7 p.m., so keep an eye out for those. Until then, I'll keep working on this rocket, and I'll see you guys next time.